Okay, good morning. We'll get started. Yes, we will. Question was, does the exam cover today's material? We're mostly reviewing. We are going to cover some new material, but it's kind of falls under the exam anyway. So even though I won't be asking you on anything on capacitance, we use a lot of the techniques that you need to be familiar with for the exam to find the capacitance of an object. So anyway, if we get into that today, then it's good review, but I won't ask you anything on capacitance. But probably the first half of the lecture for sure is review for the exam. Okay, let's start out with this one. You'll have to keep guessing. Basically, yes, we're reviewing for the exam. It's all good stuff today. All right, so if our spacing here is D, we've got this grid, we've got these charges. What's the electric field at the center? Okay. E equals 0. E is a vector quantity, right? The electric field from the charge on the right points to the right. The electric field, from the charge on the left points to the right. The one on the right points to the left. They cancel each other out. It's a vector quantity. Okay, what's the next question going to be? Find the potential. I'll give you a hint. It's not 0. Okay, we have a KQ over D from the one on the right. We have a KQ over D from the one on the left. We add them up. Excellent. Okay, let's do this one. Okay, we'll start with the easy one. I guess I should tell you here, if V equals 0 at R equals infinity. Positive Q, yeah. KQ over D. Good. Let's do this one. Q uniformly distributed over this quarter circle. It's going to be the same thing. Can you see that? Or do we have to work it out? Pick some little chunk, dq. Because the charge is all the same distance away from the point of interest, we're just adding it up. It's not a vector quantity. It's we could take it all and put it in the same place as long as it's all the same distance away. So let's work it out just to prove it to ourselves. The integral of k dq over r. R is a constant, right? It's just d. What's the integral of dq? It's the total charge q, right? If you don't see that, we could plug it in and get it. The integral of dq is lambda ds, right? And ds is r d theta. Lambda. R is d. Can I just put d there? And what happens if d's cancel? K lambda integral of theta from 0 to pi over 2 gives us a k lambda pi over 2. And what is lambda? It's q over pi d over 2, I think. And this is equal to kq over d. Okay. So work through it if you need to. Let's do one more. There's our charge distribution, Q. You got it yet? Okay. So V is not a vector quantity. We just add them up. That's nice. Except for the fact that for 2 weeks I was pounding into your head, vector, vector, vector. So you have to get over that. But you can see as long as the distance is the same, they're all contributing the same amount. Okay, let's do this one. Okay, so they give us the initial and the final. We'll just do them one at a time here. They give us the initial and the final, and we want to know what happened during that time between the initial state and the final state. Did the potential energy of the system increase or decrease or stay the same? Was the work done on the system positive, negative, or zero? Was the work done by the system positive, negative, or zero? So we're going to fill in this table plus, minus, zero, or greater than, less than, I don't know, how is it? Yeah, equals. So we're going to fill this table in. So in this case, we have a plus Q, a plus 2, and a plus 3, and we switch two of them, right? We switch those two. So the 3 is up here now, and the 2 is down here. What does that do to the system? Did we have to do work in doing that? Is there more energy stored in the system? So the energy in the system hasn't changed. If you think about, what we talked about last time, where the energy in the system is of 3 charges, it's right, it's the sum of every interaction energy, right? And nothing's happened here. By changing the place of 2 and 3, you still get the same 3 terms for the energy in the system. They're still interacting the same way, basically. So our energy here hasn't changed. This is 0. This is 0, right? Okay, let's take a look at the next one. Now we're going to, what are we going to do? Oh, we're just switching 2 again. It's an equilateral triangle. Maybe that, because it starts out as an equilateral triangle, note the spacings haven't changed. If it wasn't an equilateral triangle, then we might be doing work moving the charges around. Like down here, if we took one of these and swapped the charges, we might have a different energy. But when it's an equilateral triangle, you swap them around, all the distances are still the same. That's the key. So here, same thing, right? It's an equilateral triangle. We moved them around. Doesn't matter. Okay, now let's take a look at this one. We stretched it a little bit, right? There's this 3 coulomb, 3 plus 3 charge, and we pulled it down and stretched it so it's a little farther away from the other 2 charges. So in doing that, what happens to the energy of the system? Did we do work on the system, or did the system do work on us? Right. So the system now has the initial energy is more than the final energy. Is that what I said? The initial energy is more than the final energy. No, I think we had it backwards here earlier, right? Yeah. Initial energy is more than the final energy, because these objects repel each other. We good? So When the positives are close together, there's a ton of energy stored there because they don't want to be close together, right? So if we allow it to get a little farther apart, we've released some of that stored energy, right? There's not as much stored energy in the system now. It's like you have a spring that's coiled really tight and you let it relax a little bit. Now you have less energy stored in that spring. So the initial energy had more than the final, which means the work done on the system was negative, or we could say the system did positive work. Remember, these two always have to be opposite. If our particle starts and ends at rest, and all of these are at rest. Okay, we good now? Yeah, okay, good. Next one. Same thing. We allow that +3 charge, or we pull that +3 charge down, or we allow it to move down, whatever the case may be. But this is a little different because the other charges have changed. There's instead of a +2 as one of the upper charges, we have a -2Q as one of the upper charges. Okay, so what do we have? We've got a positive. So there's a net up here. There's a net negative charge, right? +1, -2. There's a net negative charge there. So this +3 is attracted to the net negative charge. So in order to pull it, we have to go in there and exert a force in the direction we're moving it. We have to do positive work on that thing. We have to pull it down. It doesn't want to go down, right? So we're adding energy to the system because we can let go of that charge and it's going to go back and we'll get that energy out as kinetic energy, right? So the final is greater than the initial. Or the initial is less than the final, I guess I should say. And that means we did positive work on the system, or you could say the system did negative work. Okay, one or two more here. What do we have? Now we've changed that +3 to a -3. Same situation as 4, but we've changed the +3 to a -3. So this is going to be the opposite of the previous case because we still have a net negative here, but now we have a negative here. Those negatives repel each other, and so we're allowing it to move in the direction the field is pushing it. So the field is doing the positive work. Work done by the system is positive. We have to reach in and slow it down because it would just keep going faster and faster and faster as it moved away if we allowed it to, but we want it to start and end at rest. So we reach in and have to do negative work on the system. And that means that the system has lost energy. The initial is greater than the final. Last one. Question, do these comparisons hold true regardless of the magnitude of the distances? Yes, but we're assuming that these two distances, right, this one and this one are the same, because we can just kind of combine those two into one big force. Does that make sense? If those distances weren't the same, then we'd have to do some calculations and see which one is more dominant, which one is sort of has a bigger impact on the energy of the system, because it might be closer to one than the other. So because they're equidistant, we just add those together and say it's like one big charge there. Okay, so this is the exact same situation as the previous case, right? So we have a net negative charge here. We have a negative charge here. So it's just like the previous case. Um, all right. Okay. This is for a 3-charge system, right? And remember, when you do this equation, you have to maintain the sign of Q. If Q is negative, you put a negative number in. If Q is positive, you put a positive number in, because U can be positive or negative. It could be 0. You might get, when you move, when you have a positive charge there and you move another positive charge in, you're increasing the energy of the system, right? So U's positive. But if you then bring a negative charge in, that decreases the energy of the system. So you may end up with 0. So you have to be careful with those signs. Make sure you use the correct sign for the charge. Okay, let's do a problem. Two conducting spherical shells. Inner shell has a radius R1 and a charge Q1. And the outer shell has a radius R2 and a charge Q2. Find E and V everywhere if V equals 0 at R equals infinity. Okay, so these are thin. We're not, usually when we have a shell, we say it has some thickness to it. We have an inner radius and an outer radius. Here we're saying the shells are very thin. We're just saying it has one radius. It's a very thin walled shell. So we have a circle that's something like that, and then a second one that has twice the, is that twice as big? Close enough. Okay, something like that, right? Inner shell, outer shell, R1, R2. The inner one has positive charge on it. Outer one has negative charge on it. Okay. Did you find all the E's yet? So let's start R less than R1. What's our electric field when we're inside the inner shell? Good. There's no charge inside of that shell, right? If we drew a Gaussian surface in here, there's no charge inside of our location. No electric field in there. Let's go out between R2 and R1. We're in between the shells now. What's the electric field there? Yes. We have spherical symmetry in this problem. So all the charge outside of our location, because we have spherical symmetry, cancels out. And what do we do with all the charge inside of our location? We just treat it like a point charge at the origin. So it's going to be KQ1 over R squared. And it's positive charge, so it points outward. It cancels out. You have to do the calculus to show that, right? So if you're in, so let's say we have charge evenly spread throughout the volume of a sphere. This is a sphere. Charge evenly spread throughout the volume. And we pick a location in here. We want to know what's our, we draw a Gaussian surface there, right? But what happens is if you draw two lines here, if you draw a line, any two lines through that point, you could say that this charge over here contributes a lot, right, to the electric field at the X, at our point of interest on that inner location, because it's really close, but there's not very much charge there. And then you could say, well, this charge over here is far away, but there's a lot of it. And if you do the calculus, those two exactly cancel out. All right, R greater than R2. What's the electric field? So that's negative charge. So we're in the negative r hat direction now, radially inward. Okay. So we can draw our electric fields now, right? We've got E equals 0 in here. And in between, the field points outward. And out here, it points inward, and it's half as strong. Right? Is that right? Yeah. Something like that. Okay, now V's everywhere. Where are we going to start? So it's going to, we know the answer here, right? It looks like a point charge. What's the potential from a point charge? We just add up all the charge, put it at the center. So it should be K times -5 nanocoulombs over R. But let's go through and do it formally just because it's good practice. So what do? We say we're going to start at infinity, right? And we're going to come into some arbitrary place. Any R. And we're going to use this formula. The change in electric potential is the integral of E dot ds, negative the integral of E dot ds. Okay, so we know the electric field there. We can plug it in and do that. So what is delta V? It's final minus initial. E was K minus 5, right, over R squared, dr. Now we're going, let me draw it here. We're going in this direction, but our electric field is pointing inward. So the dr and the E have an angle of 0 degrees between them, right? They point in the same direction, 0 degrees. So we have a cosine 0 degrees. And this is going to be our final, and this is going to be our initial, because we always put the smaller number at the bottom of that integral sign. Okay, so what do we get when we and so what do we know? V final minus V initial. What does that have to be? Has to be negative, because V final has to be less than V initial. The electric field points from the initial to the final place, and the electric field always points toward lower potential. So V final has to be lower than V initial, smaller than V initial. So this has to be negative. Okay, so let's do it and see if we get the answer. We know the answer already, but let's see if we get it. So our V final, well, let me just work on the right side of the equation first. I've got a minus sign. I've got a K. I've got a, oh, this should be, I see what I did here. This should be the absolute value, because I've taken into account the direction of E in my cosine theta. I'm pretty sure that should be an absolute value. And I've got an integral. If I make that negative, then I'm double counting the direction, right? You understand? And this is going from R to infinity. Although we'll find out in a minute if I was right or wrong. And see, I told you these signs are very tricky. So try your best to get them right, and then we'll fix it at the end if I'm wrong. Okay, so what do I have? I've got, I believe this is minus K times the 5 nanocoulomb. This is going to be a negative 1 over R from R to infinity. That gives us 0. So what do we have? We've got minus K. We've got the 0 minus plus 1 over R. This is just a 1 over R. So that's what I get. And it is negative because I use the absolute value of my charge. So this is negative. So we're good, right? Now, what do I get on the left side? V final is just V at any location. And V initial is V at infinity, which is 0. So this is just V at any location. This is the only equation, I think. The question is, when do we take the absolute value of the charge? I would say this is probably the only equation because we're specifically taking, where's my equation? We are specifically taking the sign, the direction from that dot product. That dot product is telling us that E is pointing in the same direction we're moving or the opposite direction we're moving. And so if we then put in a negative for E, then we're flipping it, right? We're ignoring the fact that we already took the direction into account. So in this equation, I would use absolute values. But like I said, just make sure you fix it in the end if you don't have the sign right. It's very tricky to get all the signs right.
What if the outer surface of the sphere has some thickness in it?
In this problem, no. Normally, when we do shells like this, we give it an inner radius and an outer radius, and that there's some thickness to the conductive material. That's normally the way I write these problems because they're a lot more interesting. But in this case, it just said they're very thin-walled. It was assumed that there's no thickness to it.
Right, but could you go over a scenario with thickness?
Sure. Let's do that. Let's do that. So let's have, let's add in here. Okay, I can do that, no problem. R3, so this is going to be inner So how about that? We'll give it a 2 centimeter wall thickness. So it looks like this. Did I want to do that? So now I have to change this picture. Oops. Where was it? I had a circle here. Something like that, right? Centered there. And then I had a second circle, tiny bit. Now I need a second circle, just a tiny bit bigger than that one, right? How's that? Okay, so this is R1, R2, R3. Can you read that? And in here we have E equals 0, right? E equals 0 in here. We're inside of a conductive shell, right? Okay, so we're going to give it some wall thickness. We've got E everywhere, except we have to add a case here. We've got between 1 and 2. We have to add between 2 and 3. E is 0 inside a conductor. And then this is R3 over here. This is R greater than R3. And I think everything is correct here for my E's now, right? Nothing's changed inside of that location. Nothing's changed outside. It's just in the thickness, in the wall thickness, E is 0. That's the only difference. Okay, now we're just going to pick up where we left off. We're finding V outside of R3, R greater than R3. And we know what it has to be. It has to be this value right here. Okay, so we're working our way down. And what did we get? We got that answer. So that's R greater than R3. So there's our first one. Now we keep moving in until we get to, we keep coming in until we get to the surface right here. And then we say, what is the electric potential at that surface? we just plug in the value of r at that location. It was given, what was it? 17. 32. Units. Units are a mess in this, but anyway. If you get all your units right, you'll find the voltage. Okay, so that's it there. Now we want to work our way inside. Now we say between is that good enough? Now we're going to go between the two, within the thickness of that outer shell, right? We gave that outer shell a 2 centimeter wall thickness. So we're going to go through there. So this is between R2 and R3. So we say delta V is minus the integral E dot ds. And what is delta V? It's a final minus initial. And we're going from, let me draw it first. We're yeah, close enough. We're going from here in through this shell, right? And so this is V at R3. And in here, E is 0. So that means that delta V is 0. So V final minus V initial is 0. And what is V initial? It's V at R3. So V at any R is just equal to what it was at the surface in that whole region. So remember, when E is 0, V does not have to be 0. It has to be constant. Now, 0 is a constant. It might be 0, but it doesn't have to be. It has to be constant. So in this region, we've got V is equal to minus K times 5 over 32 centimeters. Is that what it was? Yeah. Okay, 2 more regions to go. So we say at the next boundary, at R2, it's just the same as it was in that whole region, right? It doesn't change. It's the same. It's the same on the outer wall. It's the same everywhere in between. And it's the same on the inner wall of that conductor. Everywhere on that conductor, V has the same value, minus K times 5 nanocoulombs over 32 centimeters. Now we're going to go inside of that next region. So now we're in here, right? Where there's the inner one. Right? We're starting here. This is our initial. And we're going to a final location over here, somewhere, any arbitrary location. So this is our R, any R. So we say delta V is minus the integral of E dot ds. Delta V is final minus initial. Now, what is the electric field in that region? It was K Q1 over R squared, right? And it was positive charge. So the electric field is pointing outward. And we are going inward. So we get a cosine 180. And we're going from our final to our initial. Question about 30 centimeters. I think the question is about this one. Because we're finding V at location R2, but we don't plug in R2. V is not a function of R. V is constant. So it doesn't matter that we're at R2, right? We could be at 30 centimeters. 30 centimeters is 30 centimeters is here. We could be at 31 centimeters. We could be at 32 centimeters. We could be at 31 and a half, right? It doesn't matter. Anywhere on that conductive shell, the potential is the same. And this is what it is. Good? Okay, so what do we plug in here? Our final, first of all, final minus initial has to be positive, negative, 0. What does it have to be? Must be positive because the electric field points from the final to the initial, right? Radially outward. So initial has to be less than final, which means final minus initial is positive, right? This number has to be smaller than that number. So this has to be positive. Okay, so let's work on the right side of the equation. I've got a minus K. Q is positive 10, but I would use my absolute value anyway. Cosine 180 makes that a positive now. And I've got an integral dr over r squared from r to r2. And this gives me minus 1 over r2 plus 1 over r. And r2 is bigger than r, so 1 over r2 is smaller, so this is positive. That means the whole thing is positive. And what is the left side? The left side, V final, is just V at any R. And V initial is V at R2. And what is V at R2? It's right here. Negative K 5 nano over 32 centimeters. Okay, now I can bring that to the other side.
Hi, Professor.
Yes.
I get the different sign with you. Can we go through the sign one more time from the equation you have? Because cosine pi, cosine 180 is negative. So that negative with the negative before that, right, become positive.
Right.
And then the integral, y is from R to R2. I thought it should be from the initial R2 to R.
No, it's in math, you always put the smaller number at the bottom of an integral. That's what I'm told.
Oh, really? I always think it's initial to the final. Usually do integral.
Yeah, so the cosine 180 takes into account that you're going, how you're moving with respect to the field, and you always put the smaller number at the lower end of your integral sign and the bigger number at the top.
Okay, so if I do not use the cosine 180, then I can use from the initial to the end, right? Because right now it's really confusing because for this kind of case, it's hard for us to really know if it's supposed to be positive or negative. Then we really depend on the end result, then say, okay, this is big, then this should be positive. If it's not this kind of complicated, then
yeah, so
we can figure
it's
out.
This part is easy, right? To tell you whether the answer should be positive or negative. You should know whether your answer is positive or negative from looking at the direction of the electric field and how you're moving, right? So that you know whether it's positive or negative. Getting all the signs right is incredibly complicated. I agree. I try. I usually get it right because I've done this 100 times, right? But probably after I'd done it 50 times, I was still making mistakes, right? So, and then like even just before here, I almost missed the fact that I had to take an absolute value for the Q, right? So it's very easy to miss things. So in the end, make it right. If yours is negative, throw it needs to be, so mine needed to be positive. If I was off, I would just add a negative sign in here.
So during the test, if we do that, you will not deduct points for us, right?
No, I absolutely expect you to just fix it if it's not right. The sign is not right.
Okay, thank you.
Yeah. It's very hard to get those signs right. I'd much prefer, instead of you memorizing how to get the signs right, I would much prefer you just think about your answer for a second and say, wait a minute, this has to be positive, and I have to cancel this negative sign somehow. That's, to me, that's a much better understanding of the material than trying to memorize how to get the signs right. Okay, so there's our answer for the electric field. And can I just give me 2 more minutes here, and then we'll take a little break. So this is anywhere between in this region here, right? Anywhere in this region here, we just found the electric potential between R1 and R2. Now we need to go less than R1, right? So at R1, we just plug in R1 to this equation, right? K, 10 nanocoulombs, 1 over R1 minus 1 over R2 minus, why does stuff disappear? I think that was a 5 nanocoulombs, right? Okay, so that's a constant. That's the value at R1. And then when we move inside of R1, E equals 0. So V does not change. So V anywhere less than R1 is equal to a constant is equal to that value right there. So it stays constant from the surface from here all the way through. It's constant because the E is 0 in there inside of R1. Okay. Whew. We'll take a little break now, 10 minutes. Come back at what, 13? Call it 11:13. All right. Let's do this worksheet. Okay, we've got 2 hollow spheres made of conducting material. Each sphere has a different charge. One's Q and one's 2Q. So we want to find, instead of doing what they're asking for, you could do that later. Find the electric field at each location. They're ranking them. We're just going to find it. Find E at each location. These are conductive shells, hollow. The electric field at point A. is 0, right? We're inside of a conductive shell. There's no charge inside. There's no electric field inside. And so at B, same thing, right? How about D and E? Okay. Now, outside, what does this thing look like? A point charge at the origin because it's spherically symmetric. So we can treat it like a point charge at the origin. So for the first one, here's C, it's K, Q over the distance squared, goes at 3 halves R squared. 4/9, I think that comes out to. K, Q over R squared. And for F, the charge is twice as much. So it's going to be 2 times that, or 8/9 KQ over R squared. Okay. Now, what's the next question I'm going to ask you? Got to start thinking like me. Yes. So where are you starting? You're going to start on the outside and work your way in, right? If we're outside a spherically symmetric charge distribution, it looks like a point charge. And it's the same for electric potential. Looks like a point charge. And the electric potential due to a point charge is KQ over R. How about inside of that charge distribution? The electric field 0 in there. So what's the electric potential? Not 0, not VC. The potential at point A has to equal the potential at point B has to equal the potential at the surface, right? Which is KQ over R. At the surface, the potential has to be constant everywhere inside because the electric field is 0. Delta V has to be 0, correct? Okay, so how about the next one? We've got VF is K times 2Q over the distance. And the potential at D and the potential at E. K times 2Q over R. All right. Let's take a look at this situation. We'll just do A. We don't have to do it 6 times. We'll do A. So what I'd like you to do is find the electric field between the plates. Actually, what are we doing here? It says to rank the potential difference. Okay, so we're going to find the potential difference. Find the potential difference in case A. We'll just do one of them. There's the situation. We've got a plus 9 microcoulombs per square meter on the left sheet and negative 6 on the right sheet. These are infinite insulating sheets. Insulating sheets. So the the electric field from the positive plate, the positive sheet of charge, extends out in both directions. From the negative charge, it points toward the negative charge, right? And we could figure out the electric field out here. We could figure out the electric field out here, but we don't need that, right? What we need is the electric field between the two plates. And it's the electric field from the positive plate plus the electric field from the negative plate, it's vector addition. They happen to point in the same direction, so we can just add them up, but it's vector addition. Take into account the directions. And we're going to use the fact that we know, I guess I should derive this, but we've done it a few times, so I'm just going to use the fact that the electric field from the sheet is sigma over 2 epsilon naught. You can derive that from Gauss's law in a couple of lines, right? So what we want to do is add those up and get the total electric field between the sheets. So we've got the positive 9 over 2 epsilon naught, and we're going to add to that the 6 because we've taken the directions into account, right? Not negative 6. And those are both microcoulombs, so we need a 10 to the minus 6 there. And what do we get? We add those up. I get 15 times 10 to the negative 6, 2, 8.85 times 10 to the negative 12, 1 million. Roughly. The 6 is not negative because we're doing vector addition here, right? They point in the same direction. That one points to the right, that one points to the right, so they are both the same sign. This just gives you the magnitude of the electric field, right? This is a vector quantity. That's the magnitude of the field. You have to figure out where you're standing, right? If you're standing over here, it points to the right. That's our positive x direction. If you're standing over here, it's negative, right? So the formula doesn't know where you're standing. You have to assign a direction to it after you find the magnitude. All right, so now we say delta V minus the integral E dot ds, and E is constant everywhere in there. So this is just and the distance was given 8 centimeters. About 80,000 volts. Which one's at higher potential? The left plate. Correct, because the electric field points to the right. Okay. I've got a cool application of electric potential I want to show you. I'll share this video with you. Okay, so check this out. This is a table saw. That circular blade spins at over 3,000 RPM, and if things go wrong, they can go seriously wrong. This invention, the SawStop table saw, can help prevent serious injuries. Let's see how.
We designed this saw to be the safest table saw ever built. I think of it like seat belts or an airbag for table saws. The mechanism is very sophisticated, but the technology behind it's actually quite simple. The blade carries a small electrical charge. This charge is continuously monitored by a digital signal processor. When contact is made, the human body absorbs some of the charge, causing the voltage to drop. The drop in voltage triggers a quick-release aluminum brake. A heavy-duty spring forces the brake into the teeth of the spinning blade. The teeth dig into the aluminum, stopping the blade cold. The blade's momentum forces it to retract below the table, and the motor is automatically shut off.
Once more in slow motion, and again in regular speed. This is the culprit that tripped my SawStop. It's part of a hockey stick. Hockey sticks are made of carbon fiber, and they are conductive. Amazingly, that's the only scar left on this stick before the safety mechanism tripped. Here's the actual safety mechanism and blade from that incident. You can see where the blade cut into the aluminum and stopped suddenly. The aluminum is even melted onto the blade. All of that happened in about 2/100ths of a second. Okay, that's pretty cool. I have a question for you. What happened to the blade? Once more in slow motion. The blade retracted. Why is that? And again in regular speed. It's spinning at 3,000 RPM about, and it stops suddenly. That's a ton of angular momentum that's built up that has to be dissipated so it doesn't damage the saw. So the whole arm, there's an arm mechanism where so the spinning blade is mounted on an arm. When that spinning blade stops, the whole arm swings to dissipate some of that angular momentum, to allow the angular momentum to dissipate over a longer period of time. And that's why the blade, when its blade stops, the whole arm pulls and it retracts below the table. It's a conservation of angular momentum. Okay, let's see. What do we have here? So they put some voltage onto the blade, some electric potential, right? They put a small signal onto the blade. Now, when that small signal is enough to keep the blade at a certain electric potential, whatever, 2 volts or something, then your body touches the blade, your body's slightly conductive. That signal then is dissipated not just over the blade, but over your whole body as well. So that 2 volts then drops. It's whatever they're supplying is not enough to maintain you and the blade at 2 volts. That 2 volts drops, and they can detect that. The blade cannot be used again, and the safety mechanism cannot be used again. The safety mechanism costs about $80. That little spring-loaded chunk of aluminum, you have to replace that. The blade, you'd have to replace that. That also, it depends on how much your blade could be anywhere from $40 to $100. But you're up and running again in in 5 minutes. It takes about 5 minutes to swap it out, and you'd be up and running again with maybe a Band-Aid on your finger, and instead of a trip to the emergency room. Now, actually, I forgot to put it in that video. I'll have to redo this. Let me show you this. Let me show you the graph of electric potential on that blade. It's impressive. Let's see, where are we? Lecture, E&M. I have to share this with you. Hold on. Okay, so the potential is nice and constant. I don't know if you can see that. It's nice and constant. And then, where's my blade? The blade has teeth all around it, right? Let me grab my blade. Hold on. This blade has 50 teeth. 50 teeth all around a 10-inch diameter blade, right? So there's every centimeter along here, there's a blade, a cutting tooth. This is spinning at 3,000 RPM, right? What happens is when the first tooth makes contact with the finger, the electric potential starts to drop. And for a fraction of a second, about 100th of a second or so, you're in between. The first tooth is now no longer touching your finger, and the second tooth hasn't quite touched it yet. The potential starts to go back up at that in between. Then the second tooth makes contact with your finger, and the potential drops again. And that's a real clear signature that they look for. And that's what trips that the safety mechanism. So it really impressive. That all happens in like 2/200ths of a second. It is pretty amazing. The saw, there's nothing, the saw is undamaged. The blade and that aluminum chunk come together, and both of those are damaged, and they pop out. You pop a new blade in, a new safety mechanism in, and like I said, in 5 minutes, you'd be up and running again. That guy actually is a physicist. He got his PhD in physics at UC San Diego when I was there. So our paths crossed there in San Diego, and now he's making table saws. He actually became a patent attorney. He got his PhD in physics, became a patent attorney, because a lot of patents are technology related, right? So patent attorneys that understand technology are very valuable. So he made most of his money as a patent attorney. I'm not sure which business does better for him now, SawStop or being a patent attorney. Okay, so where are we? We're going to start capacitors. That's where we are. Okay. So what is a capacitor? Basically, what we do is we take two conductive pieces, two conductors, and we hook up some kind of a potential difference between them, right? A battery or a power supply. And that battery pulls an electron off of one plate and moves it around and deposits it on the other plate, right? So you could think of negative charges as moving in this direction, or if you prefer, positive charges as moving in that direction. But really, we know it's plucking the electrons off of the left plate, moving them around and depositing them on the right plate. So it pulls an electron off the left plate, which means there's now a net positive charge on that plate, and it sticks the electron on the right plate. And so now there's a net negative charge on that plate. So you could imagine if we have a very weak battery, just a small delta V, whatever, 1 volt battery we stick in there, our power supply, we turn our power supply to 1 volt, and it moves a few charges around. And then that battery is not going to be strong enough to move any more events, because think about what it's doing. It's taking an electron away from a plate that's positively charged, right? So it has to pull a negative away from some positive charges, and then it has to stick it onto a plate that already has negative charges. They are repelling any new negative charges to get there. So the battery moves charges around until it can't move them anymore, and then it stops. So if we were to measure the charge, let's call this plus Q and this minus Q. If we were to measure the charge, Q, as a function of that voltage, it would increase. We'd turn the voltage up a little bit and we'd get some charge there, right? And then we'd turn the voltage up a little bit more and we'd get some more charge. And then we'd turn the voltage up a little bit more and more charges would move around, and then the battery would stop moving the charges because it couldn't push any more negatives onto that negative plate. But then if we cranked up the knob and turned the voltage up a little bit, we'd get some more charge. And so we could keep moving charges over as long as we could keep cranking up the electric potential between those plates. And what we get is roughly a straight line. Well, we get a straight line. So the charge is proportional to delta V, right? And in order to make it an equal sign, we have to throw some proportionality constant in there. So the slope of this line is that proportionality constant, right? C. We call that the capacitance of our capacitor. So this is a capacitor, and a very common capacitor is two parallel conductors like this. It's called a parallel plate capacitor. But it doesn't have to be parallel plates. It could be a cylindrical conductor inside of another cylindrical shell, right? It could be a spherical conductor inside of a spherical shell. It could even be just one conductor, and we assume the other charge is at infinity, but usually we have two conductors. Okay, so parallel plate, very common configuration for a capacitor. So C is our capacitance. And what does that depend on? It only depends on the capacitor. So what does that mean? The shape, the size, the spacing between the plates, things like that. So this capacitor, people say that a capacitor stores charge. That's sort of a loose way of saying it, but if you think about it, it's not really storing charge, right? The charge was always there. We just separated it. It stores energy, right? It stores energy between those plates in the electric field between the plates. We've done some work on the capacitor, moving the charges from one plate to the other, and so that energy is stored in there, and then that's one use for a capacitor. So a lot of times when you have a some older cameras, the flash on the camera required a big current in a small amount of time. Well, in order to get a big current in a small amount of time through that flash bulb in the camera, you'd have to have a really big battery. Well, you don't want to lug around a really big battery. So what it did instead was it had a small battery that charged a capacitor. And then once the capacitor was charged up, you could discharge that capacitor very quickly. You can't get the current out of a battery very quickly because it's limited by the chemical reaction in the battery, right? There's some time it takes to get the charges out of the battery. But the capacitor, you can discharge very quickly. So what the camera would do is it would charge up the capacitor, then you could take your picture, that capacitor would discharge through the light bulb. You get a huge current through the light bulb and it make it flash. Then if you wanted to take another flash picture, you had to wait for that capacitor to charge up another, 10 seconds or something for that capacitor to charge up. Then you could take your next flash picture. You couldn't take them one right after the other. So that's kind of an example. So storing energy is one example, but you can also use them in circuits to make the circuit react a certain way. We'll get into that later. Okay, so let's find the capacitance for a parallel plate capacitor. I already told you it depends on the properties, the physical properties of the capacitor, right? Size, shape, spacing, things like that. So let's see what it is exactly for a parallel plate capacitor. So what we are going to do is try to solve for, we know this equation is true, right? Q equals CV. That's our equation for a capacitor. The charge, we say the charge stored, but it's the charge on each plate, how about that, is equal to the capacitance times delta V. So we're going to find delta V for this configuration in terms of the charge, and then compare it to this equation, Q equals CV, and figure out what C has to be. Does that make sense? So we want to find delta V in terms of Q. Well, what equations do we have? We have this equation. Delta V is negative the integral of E dot ds, right? That should look familiar. And we know that E, for an infinite sheet of charge, right? What does E depend on? It depends on the charge on that sheet, right? The charge density. So if we plug in E in terms of the charge that's in this capacitor, and we do this integral, then we'll have delta V, and we'll have hopefully Q or sigma or something in there that reminds us of charge. And then we can figure out what the capacitance is. So let's do that. So the first thing we need to do is find E. So we have a capacitor. Got positive charges on one plate, right? Negative on the other plate. And we have an electric field in here. And so what do? We pick a Gaussian surface that looks kind of like this. And we say, the integral E dot dA over all the surfaces that make up our enclosed Gaussian shape has to equal Q inside over epsilon naught. And what do we end up with? We end up with the integral over the left side of our Gaussian plus the integral over the side, the curved side of our cylinder, plus the integral over the right face of our cylinder has to equal Q inside over epsilon naught. Now, is there any flux through the left face? It's inside. I drew it inside of the conductor. So there's no flux through it. And there's no flux through the sides. So all I'm left with is the right face, and that's E times A. So I have E A is equal to Q in over epsilon naught. And what is Q in? It's the area times our charge density. So this is sigma charge density . Question is, how is energy stored in these between these plates? Well, you're doing work on them, right? So, I mean, if you have a mass and you lift it up to a higher location and set it there, you've got stored energy now, right? You did some work on that mass, lifting it in a gravitational field. Now you have some stored energy there. If you let go of it, what's it going to do? It's going to drop, and you get turn into kinetic energy, right? And the same with charges, right? If we have a positive charge sitting in an electric field and we move it opposite the direction of the electric field, we've stored some energy. We've increased the energy, the potential energy of the field charge system. And if we let go of it, it's going to start moving in the direction of the field, and we'll get some energy out, right? We'll get some kinetic energy. Well, the same thing happens here. In order to get those charges, all those negative charges in one place, those negative charges don't all want to be in one place on one sheet. In order to get them that way, we had to do work. We had to move them around doing work, pushing them onto that plate, doing work. And now it's stored in there. If I take the battery away, those charges are separated. They don't want to be separated. All those negatives want to repel each other and go back to the other side. So we've got that stored energy. If we hook up a light bulb between those two plates instead of a battery, those charges are going to run through the light bulb, and the light bulb is going to give off its energy. It's going to dissipate some of that energy. What is Q? What is sigma? Sigma is the charge divided by the area of that plate, right? However big it is. Q over A. Total charge over total area, right? So this is good. The A's are going to cancel. And then my E is going to be Q over epsilon naught A. That's the total charge on one plate. That's the area of the plate. So now we know E. Now we can figure out, and it should be constant, right? We know the electric field's constant next to an infinite sheet. And that's how we deal with it. We know this is not infinite, but the plate area is pretty big, and the spacing between those plates is pretty small. So for most of the time, right, I know the wall behind me isn't infinitely big, but if I put my eye 1 inch in front of the wall and I look to the left and I look to the right, it looks like an infinitely big wall, right? If I'm close enough to it, I can't really tell the difference if I was standing in front of an infinite wall or that one, right? So that's the way it is with the geometries in a lot of these. The spacing is quite close together between the plates, and the plate size is fairly large. So for most of that volume between the plates, it's as if those plates are infinitely big. It's not a bad assumption or approximation. Okay, so now we want to find V. Oops, I'm way over time here, aren't I? Sorry about that. Lost track. Give me one more minute. Delta V minus the integral E dot ds. I plug in E. And E is constant. So this is just minus E times the distance between the plates. And so I've got delta V is, and I don't care about the minus sign. I'm just going to do here, let's just do there. So I want to compare this. What's my equation? Q equals C delta V, right? That's my equation I'm trying to get this to. So I'm going to move stuff over. So I'm going to have epsilon naught A over D times delta V is Q. And I know Q has to equal C times delta V. So what is this? That must be the capacitance for a parallel plate capacitor. Okay, so we found the capacitance, and it's using these techniques. So you can see what's our next chapter we're doing? Capacitance. How are we going to be finding capacitance? Using the stuff that you have to know for the exam on Friday, right? Delta V is negative the integral of E dot ds, finding the electric field due to charge distributions, using Gauss's law, stuff like that. Okay, I will end this meeting. Sorry I went over, and I'll stick around for a couple of minutes. Our lab is relatively short.